whenever time gets, you can just refer this lecture also. Okay, I'll be posting in Google Classroom also. So I'll be directly jumping into the lecture. So the topic is the unit topic is semiconductor devices and its application. In this unit, most of the semiconductor devices, particularly with respect to your diodes as well as your BJT switches, okay, will be covered, and application will be seeing with respect to your rectifier. The rectifier point of view, will be seeing the applications. Okay. So in today's lecture, we will be covering up to your PN junction diode. Okay. So here you already know the classification of semiconductors, right? So the classification of semiconductors but mainly is based upon your what you can say upon the type. Like it is called as intrinsic semiconductor and extrinsic semiconductor. So how we can say this to be intrinsic semiconductor? So we can say it to be as an intrinsic semiconductor one and only if pure semiconductor is there. If you are having a very pure semiconductor without any doping. So I hope you remember doping. Doping means adding impurities to your pure semiconductor. So if it is not doped means, then it is a pure semiconductor. Okay, so this is called as an intrinsic semiconductor. So at the room temperature, the valence electrons will be able to occur. So valence electrons means you have to recall. Valence electrons is nothing but the outermost electron. Outermost electron in an atom. Okay, this outermost electron will be able to acquire sufficient energy to enter from conduction band to form free electrons. So hope you remember the conduction band and your conduction band as well as the valence band. Okay, so when if the electron is moving from a conduction band towards your valence band, then what happens? Then there will be the conduction process takes place. How it takes place? Mainly due to the free movement of these free electrons. Okay, so under the influence of electric field, the electrons will be able to constitute current. So already you will be having an atom. So on the atom there will be a valence electron. So you are just energizing the free electrons. Then there will be the flow of electric current. So this is what happens in an intrinsic semiconductor. So moving to the extrinsic semiconductor, what happens? It is pure silicon or germanium, but has a little. So here, what you have to remember is that you will be dope or add. Dope in the sense adding. Okay, you will be adding silicon or germanium to form an impure semiconductor. That's it. So that is the intrinsic semiconductor is a pure semiconductor. But if you are adding silicon or germanium to this intrinsic semiconductor, so as I said, it is called as doping. Then it becomes an extrinsic semiconductor. So upon adding the impurity, basically what happens? The characteristics changes. Okay. So what does the characteristic change means? You have to see whether it supports the flow of electric current or whether it opposes the flow of electric current. So if you are adding impurity means it supports the flow of electric current. So it is a very good characteristic for a conductor. Okay. So the semiconductor which are doped will be having a very high conductive characteristics when compared with that of your pure semiconductor or your intrinsic semiconductor. Again, this extrinsic semiconductor can be classified into two types. Either it can be a N type or it can be a P type. So now you might be raising a question. So what is the necessity for adding only silicon or germanium alone to the semiconducting material, why can't we add any other elements like sodium, lithium? Why can't we add? Okay, so the thing is that these are the elements which are more suitable to form covalent bonds. Okay, I hope you might have studied about covalent bonds, ionic bond. Okay, so these silicon or germanium will be more easier to form covalent bond with the semiconducting material. So because in the covalent bond, what happens is the valence electron sharing takes place. So what happens if the sharing takes place? The configuration will be more leading to a stability of the system, stability of the atom. Okay, and that's the main reason for selecting this silicon or germanium. Coming to the N-type and P-type. So the N-type and P-type is divided based upon the formed by the impurity atoms. So what are the impurity atom we are doping? So based upon that, this N-type and P-type is classified. So if you are adding a pentavalent impurity atom, okay, like arsenic or antimony or phosphorus, at a very low level in silicon or germanium. So these are the impurities, and this is the semiconducting base. So if you are doping these impurities over this base means, then it corresponds to the N-type. Okay, so this process creates excess of unbound electrons. So here unbound electrons in the sense free electrons. So unbound electrons in the sense free electrons. Okay, so coming to the P-type semiconductor. So here what happens? A small amount of trivalent impurity. So trivalent, pentavalent. What is the difference? So pentavalent in the sense at the valence shell. So you might have heard about the valence shell, that which is nothing but the outermost orbit in an atom. So the valence shell will be having 5 electrons revolving around it. In the most of the cases, the valence shell will be 8 electrons. But in case of the pentavalent, the valence shell will be having 5 electrons within it. Okay. So this arsenic, antimony, phosphorus will has the configuration of pentavalent. At the same time, trivalent in the sense, it will be the valence shell will be having 3 electrons. So the materials include aluminum, boron. Okay, this will be added to form the P-type semiconductor. Actually, the impurity atoms that accept electrons from valence band creating holes. So here is what you have to see. These holes are called as acceptor atoms. So what electrons does, what N-type does, it was able to provide you with the excess 1 electron. Whereas P-type, if you are having a P-type means it is able to absorb an electron readily. Okay, it is able to absorb an electron readily. Whereas the N-type, it is able to donate donate an electron readily. So that's the difference. On the N-type, there exists excess electron, whereas for the P-type, there is one. It is ready to accept the electron. Okay. And now you are just combining this P as well as N. Okay, to form a PN junction diode. So this is what the configuration is. Okay. So the PN junction diode is formed by the N-type and P-type semiconductor crystals. So if we are joining P-type as well as N-type in the sense, at the center part there becomes a depletion layer. Okay, so we'll be seeing about it. I hope you have studied in the previous classes itself, but I'll be just recalling it. So adding acceptor impurities to a wafer or donor to a P-type wafer. So how it is formed, they are just saying. So to have a simple idea, you're just taking a P-type material, you're just taking an N-type material and you're fusing them together. That's it. So the N-type material has a high concentration of free electrons. This we already know. Right in the previous slide I said, the N-type will be having a excess of free electrons. Okay. Whereas, so that's what over here. So that's what over here. And whereas the P-type material has a high concentration of holes. So this is the acceptor ion. So here you have to be very clear. This negative part you shouldn't be confused. Okay. So this negative is nothing but the ion which is accepted from this donor. Okay. So atom is stable only if it has both positive and negative. So if you are just separating both the proton and electron, in the sense the atom will not be in stable. The atom will not be in a stable condition. So that what I hear it happened. So the donor was able to give, this is the N junction. So that is N type. The donor was able to provide you this acceptor with the ion. So that is what this acceptor ion. So this acceptor ion is responsible for filling this hole. Okay. So that's how it goes on. So other junction, there's a tendency for free electrons to diffuse over the p side and holes to n side. So that's what I just said now. So this is the junction. So already there is holes and already there's excess of electrons. So if I just adding or diffusing both of them together, there occurs a process called diffusion. So both things will be able to combine together to form the depletion layer. So the electron, if this depletion layer is a thing where both your negative and positive ions will be combined, and this depletion layer will be more stable. In order to have a conduction from your anode, this p type is called as anode and n type is called as cathode. Not to have the conduction from your p type to n type, what will be generally doing is it has to break this depletion layer. This depletion layer has to be broken down. Okay, such amount of electric field has to be applied. Okay, so here the electrons coming into the p material combine with the holes of the acceptor atoms. So that's what I have said already, creating a negatively charged layer of unneutralized acceptor. So if these sentences are confusing you, you just have this in the mind, the concept what I have said. Okay. Similarly, the holes moving into the n material combine with the free electrons. It combines with the free electrons. So in these two para, they are speaking entirely about this depletion layer. Okay. So how this junction depletion layer is formed, they are just saying. So an arrow with a fixed positive charges. So that's what over here. So here you can see the holes have been moved over here, and here you can see the electrons have been moved over here. So the fixed positive charges on n side. So that is this side. Here it is the positive, and here it is the negative is formed. So this region is known as a depletion region or space charge region. So you have to be very clear. So in the exam point of view, they might be asking either depletion region, asked to explain depletion region, or they'll be confusing with you with these names, space charge or transition region. Okay. So this creates built-in potential, which is called as the barrier potential. So in order to have a conduction in a PN junction diode from anode to cathode, you have to eliminate this depletion layer. So in order to have eliminate this depletion layer, for germanium, you have to apply a voltage or the electric field above 0.3 volt. Whereas in case of silicon, you have to apply a voltage above 0.7 volt. So these are the characterized voltages, barrier potential voltages of silicon as well as germanium. Okay, it is already in the nature. Okay, so this is what they have already found out. Okay, so now moving on, forward bias. So what do you mean by forward bias? So forward bias of a PN junction diode is nothing but establishing positive potential of battery. That is, it is nothing but from if the electric field flows from the anode to cathode, okay, or from the p type to n type. If the electron flow is from the p type to n type, then it corresponds to the forward bias. Okay, so for this to happen, you have to break this depletion layer So the depletion layer potential has to be greater than that of the applied potential. Okay, so here you will be applying the potential. Here's the negative and here's the positive. So you'll be applying positive over here, and if your voltage is above 0.7 or 0.3 volt, then this PN junction will conduct. So under forward bias condition, the applied positive potential repels. So this is the positive potential. So here this repels all the P type. So here there is the holes in the P type. These holes will be repelled towards this particular depletion layer, and this electrons over here will be absorbed by the holes, and the depletion layer, it will be slowly decreasing. Okay, first if it was in this much length, means it will be slowly decreasing in this much length. So if the entire voltage is applied above 0.3 or 0.7, then the entire depletion layer will be diminishes. Okay, so that's what given over here. So there's a great enhancement in probability of majority carriers moving across the junction, resulting in an appreciable current flow. So that's what I said. In order to have a current flow, what you have to do is you have to always give the voltage higher than that of the depletion layer from your anode, that is your P-type material, towards your cathode. The conventional current flows from positive terminal of battery across the P to N junction and to the negative terminal of the battery, and this is called as your forward current IF. So coming to the VI characteristics. So we are studying about the electronic devices. So each and every electronic device has some kind of characteristics. Okay. So in a class itself, we can just say, if we can just take a student and we can just tell him how he's good or how he's performing well or not. Okay, how we can say means by his characteristics, how he's attentive in the class, how he's responding, how he's doing in the exams. So using that, we can tell about the characteristics of a student. Similarly, each and every electronic device will be having a characteristics. So without knowing that characteristics, we cannot use that particular electronic device. Okay. So similar to that, this is mainly based upon the voltage and current. For all the electronic device, the characteristics is mainly dependent upon this voltage and current. Okay, so the voltage will be at the x-axis and the current will be at the y-axis. So what happens as the forward voltage? So VF corresponds to your forward voltage is increased. So forward voltage means it's nothing but the voltage that we are applying over here. Okay, don't get confused. Okay, is less than the VB. VB in the sense it's nothing but the breakdown voltage. So we have seen, right, breakdown voltage. Breakdown voltage means 0.3 for germanium, 0.7 for silicon. Okay, so it is obvious that if your forward voltage what you are applying, it is, if it is less than your VB, there won't be any current flow, because the potential over here is not able to break the depletion layer. It's not able to break the depletion layer. So what happens? The current, the forward current IF, the forward current IF will be, that is flowing from your P to N, will be 0. Okay, because there exists your depletion layer, and hence it is 0. Okay, but what happens if it is going above 0.3 or 0.7? Okay, what happens if it is going above 0.3 or 0.7? Then there will be the rise in your forward current IF. Okay, So that too, this rise will be in terms of milliamps. It will be in a very small magnitude. Okay. If Vf is greater than Vb, then the potential barrier at the junction will be completely disappearing. This I have already said. If it is greater, this depletion layer will be slowly minimizing and it will be completely disappearing. And it will be disappear, and hence the electrons across the junction, the opposite direction. This will be resulting in the current flow, and then your forward current will be increasing drastically. But what you have to infer is that this graph is not a linear graph. So it is exponentially increasing graph. So linear means it will be have a very steady slope. But over here you can see the slope is not steady. It's more or less like a parabolic. Okay. So coming to the second condition, which is nothing but the reverse bias. So reverse bias is nothing but the opposite of your opposite of the forward bias. If an external voltage is applied to PN junction such that the positive terminal of the battery is connected to the N, will be just interchanging the polarity of the battery, and the negative terminal of the battery is connected to P, then it is called as reverse bias. It is obvious that under reverse bias condition, the majority electrons which move away from junction are attracted. So this is what happens. So the majority carriers, the majority electrons which move away from the junction, okay, the electrons which move away from the junction are attracted by the positive terminal at the end side. So here, so already there will be positive terminal. This will be attracting these electrons, and similarly the majority holes are attracted towards the negative polarity of the battery connected to the P side. As a result, the number of uncovered positive ions in depletion region and N-type material and uncovered negative ions in the P-type material will increase. So what they're saying is that you are at the reverse bias, you are just boosting the depletion layer. You are just increasing the strength of this depletion layer. Okay, how we are increasing? By you are forming a very strong bond between your electrons or holes in this depletion layer. So this width of the depletion layer increases in the reverse bias. So that's what given here. The net effect is widening of the depletion layer. So there won't be any current flow in your reverse bias. Okay. So this you have to see through. The PN junction diode is able to conduct only in the forward bias, whereas the reverse bias it doesn't conduct. But there will be a small flow of current. So that's what they're saying. The minority carriers, however, will cross the junction. So it has been crossed at the reverse bias voltage and contribute to the reverse current. So this is the reverse current. So this reverse current magnitude will be very low in terms of micro, 10 power minus 6. Okay. So here, the current that exists under reverse bias condition is called reverse saturation current. So the magnitude of this reverse saturation current will be depends upon the junction temperature. Junction temperature means this depletion layer they are saying. So now we'll be seeing the VA characteristics under reverse. For a large applied reverse bias, the free electrons from the N-type region will move towards the positive terminal of the battery, acquiring sufficient energy to move with high velocity. So you just stick with this point. Okay, you just stick with this point. You don't get confused by this point. So what happens for the reverse bias? There will be a small flow of current in terms of microamps. It is called as reverse saturation current. So that alone you just have it in your mind. Okay. So why there is a very small amount means due to the higher depletion width, depletion layer width. Okay. So some of the diode application. So we have seen about the PN junction diode. So where it is used, where this PN junction diode is used, this is used as rectifiers, power diodes in the DC power supplies. Okay, as signal diodes in communication circuits. In most of the mobile phones, you can see these diodes. As Zener diodes in voltage regulator, we will be seeing about Zener diode in the next slide. And this is some of the application that you can just go through. So we have to see about the breakdown. I have already said here, whenever we are applying the enough voltage to come over this particular depletion layer, there occurs the electric flow from your anode to cathode. And that is called as nothing but your breakdown. So that process is called as breakdown. So what is diode breakdown? So as the reverse bias voltage increases, the depletion layer widens and the barrier voltage rises. So this you already know. So this effect causes diffusion current to decrease. Okay. So there exist two currents, diffusion current and drift current. Okay. So that you might have studied in your physics. Okay, that expression and all will be coming with respect to the diffusion current and drift current. So I will be getting more towards that point. So what is diode breakdown alone? I'll be saying as this process leads to the widening of the depletion layer, so this depletion layer will be continuing until you're keeping your diode in the reverse bias. So that you already know. But it also has some limit. Okay, the reverse bias condition also, there exists some limit. The electronic device will be having some limit. So what is the limit? The limit is that until sufficiently high junction voltage will be developed, until the sufficient amount of high voltage is developed, then a new mechanism is set to supply. So there are just two things what you have to see through regarding the breakdown. So the breakdown will be able to occur in the forward bias also. In the forward bias, the breakdown will be able to occur and the depletion layer will be minimizing. Whereas in the reverse bias, the depletion width will be rising, but it will be rising up to a particular point. After a particular point, there exists a drop across this depletion layer. And if this drop is very high, then there occurs a breakdown. So that's what they're saying over here. Until sufficiently high junction voltage develops. Okay, a new mechanism is set to supply the charge carriers. So the new mechanism is nothing but the breakdown. So the two possible breakdown mechanisms are Zener mechanism or your avalanche mechanism. The Zener breakdown and avalanche breakdown. So this also you might already study in your 12th physics. So the avalanche breakdown occurs when the accelerated 3 electrons acquire sufficient energy to ionize a lattice atom of bombardment. Okay. So this definition is nothing but when the accelerated electrons acquire sufficient energy, in the reverse bias, there exists the accelerated electrons in the depletion layer. So if it occurs sufficient energy, this will ionize the lattice atom. So lattice atom in the sense here, you can just take the free atom. Okay, by bombardment, the additional free electrons created in this way. So by bombardment, the electrons will be coming out, will be accelerated by the reverse field, causing more and more ionization. So here in the avalanche effect, more and more free electrons will be occurring, which is responsible for ionization process. So this entire thing, what I am saying, it is in the reverse bias. Don't get confused. We are speaking entirely about reverse bias. Okay, coming to the Zener breakdown, is fun. It is different from that of your avalanche breakdown. So how it differs is that the electric field in the deflection layer increases. Okay, it can break the covalent bond and generate the electron hole pairs. So there raises two things. If the energy increase or the free electron process production is entirely based upon ionization, then it is entirely based upon avalanche effect. At the same time, if it is based upon the covalent bond, breakage of the covalent bond and generation of new electron hole pairs, then it is your Zener effect. So these two are entirely related towards your physics point of view, but you have to know about these two breakdowns. These two breakdowns you can surely expect in your exams also. Okay, so we'll be dealing with the Zener breakdown and we'll be closing it. So here, Zener breakdown is more or less similar to that of your PN junction with two special abilities. Okay, so this is called as a voltage regulator. This Zener diode is called as a voltage regulator. Why it is called as voltage regulator means it can able to control the voltage. It can able to control the voltage as per our needs. Okay, so the Zener diode is a silicon PN junction device. So for okay, this Zener diode, PN junction diode, how you can visualize is that you can visualize a normal pipe. Okay, a normal pipe you just take, and within that pipe you are connecting a tap. You are connecting a tap. Okay, so this tap will be giving out water. Okay, will be giving out the water flow, or there will be water flow only if you move that top handle of the tap. Okay, you have to rotate in clockwise or anti-clockwise direction to open the tap. Okay, then only there will be electron flow. So the same thing you can imagine over here. How means the water flow can be visualized towards electricity flow. Okay, so the tap upper part you can visualize to a depletion layer. If you are minimizing this depletion layer, then there will be the electricity flow. If you are opening the tap in the anti-clockwise direction, then only there will be water flow. So the same concept. The same concept is for your Zener as well as your PN junction also. Okay. So here it is a silicon PN junction diode, which differs from a rectifier diode in the sense that rectifier diode means normal PN junction diode. In the sense that it is operated in the reverse breakdown region. So that's the difference. So in the PN junction diode, what we have seen was you cannot operate it in the reverse bias condition. Okay, if you are operating in a reverse bias condition, what happens? There will be only a very less magnitude current flow. There will be a very minute less magnitude current flow. Okay, so the breakdown voltage of the Zener diode is set by carefully controlling the doping level. Okay. The same thing. So here, what they're saying, the breakdown level of the Zener diode is set carefully by controlling the doping level. Means you can just imagine the doping level to the opening and closing of the tap. Okay, so this is what happens in the reverse bias with the Zener. The forward bias characteristics will be the same as that of the PN, whereas in the reverse bias, this is what it happens. So over the PN, it was able to operate in terms of the microamps, but over here it is operating in milliamps. The Zener, it is operating in milliamps. So as the reverse voltage is increased, the reverse current remains negligible, small up to the knee of the curve. So knee of the curve means this P point. So up to this P point, there doesn't occur any breakdown. That is, the conduction is not significant. Whereas after this knee point or the breakdown point, the current starts to increase drastically. Okay. At this point, the effect of breakdown process begins. From the bottom of the knee, the breakdown voltage Vz remains essentially constant. This ability of diode is called as regulating ability. So other things you just see through. This is what with respect to your Zener diode, okay, and how we are overcoming this breakdown. So it's told in this particular para. Okay, so with this I'll be stopping for today.